let's do a sound check and also check for video. I can hear audio coming in just fine. Let's get you switched out. And can I see my hand moving over there? Yes, I can. Okay, then we are good to get started. Oh, I forgot to put those away. Hold on. I'm gonna need a couple minutes. Okay, I think that will do it. So, not as prepared as I would like to be, but we'll figure things out as we go. It wouldn't be the first time that I do this. In fact, a lot of my tutoring sessions tend to be like that. Students show up and I'm expecting to cover one thing, and then they'll say, can we actually cover this topic instead? And yeah, once you have enough experience, you can do that. You can just adapt on the fly to whatever you're asked. For those watching who are considering a career in tutoring. Anyway, what do we have for today? So last time, oh, and I didn't even open the assignments. That's how unprepared I am today. Let's go ahead and switch over to our course plan and let's see what we have for today. So I wanted to do, let me think. Last time we did some of these 2D force problems. And yeah, I left this as homework. Okay, it's coming back to me. And then we also said that we were going to cover forces on systems of objects. So I'll open that up, though I'm probably going to pick problems from my book, which I need to go and grab, by the way. That's another thing I'm forgetting. Because you already have the solutions for these. The solutions for these are in the video linked in parentheses. So I don't want to dwell on those too much. And let's see, we already did friction, I'm pretty sure. Oh, okay, systems of objects, but adding friction to the mix. Okay. And then we're probably going to make it far enough to cover the topic of inclined planes. Yeah, so that'll be the plan for today. Okay. Then, yeah, I guess without further ado, let me go grab my book and then we can get started. Book has been acquired. We'll put that over here for later in case we need it. Okay, pens. Here are my pens. All right, so, and I'm getting that weird error message in the chat. I don't know what is up with that. I hope it doesn't mean that people are trying to chat and it's just not letting them. I'm gonna have to investigate that. At some point. It's just these past couple weeks have been so busy I forget to do these sorts of things. They just fall by the wayside. But anyway. So I left us off with, where was it? This. I left us off with this problem over here. Actually, let me arrange these in order. 15, 16, 17, 8. Oh, and right, 18 is a different kind of exercise. That's why it's not here. Okay, so this one. Two pirates are trying to salvage some treasure from the ocean. They get the treasure onto a wooden plank with cables and pull on the cables. The pirate shown in red creates 800 newtons of tension in his cable. At an angle of 78 degrees above horizontal, the pirate shown in orange pulls on his cable at a 63-degree angle. The plank doesn't wobble, its motion is completely vertical. And there's a reminder that the plank and the treasure move together, so they should each have the same acceleration. And the questions are, what is the force of tension in the orange pirate's cable? Part B, what is the acceleration of the treasure, and will they get the treasure or will it fall back into the ocean? And part C, what is the normal force on the treasure? So those are the three questions. Let's go ahead and see what we can do with that. And yeah, if the lighting is looking a little bit different today, that's because I decided to attach my lamp on the other side of the table compared to what I was doing the last 2 or 3 times. I feel like this angle might work better, but we'll see. I'll have to look at the footage and compare, if I even have time for that. But anyway, let's draw the diagram. So, well, we've got 2 objects really, so I'll draw the overall diagram first, containing both objects. So you've got an 80 kilogram treasure on top of a 20 kilogram plank of wood. And then you've got 2 cables. I guess I'll draw those in a different color. Let's do pink. And what were the angles? 63 and 78. 63 on the right, so something like this. We'll call that a 63-degree angle. And then 78 degrees, so even steeper than that. Perhaps something like this. Not drawn to scale because I don't know which of the 2 tension forces is bigger. Actually, I think I do know. I think it's going to be this one, and you'll see why in a minute. Unless my quick math is failing me. This one would have to be the bigger one. Okay. So they said the pirate in red creates 800 newtons of tension in his cable, so I guess I'm going to call this force of tension left, even though it's not completely to the left. I'm going to call it force of tension L, since it's on the left side of the diagram, equals 800 newtons. And then over here, force of tension right is going to be some other value. Has to be greater than 800, so if I was drawing to scale, I would actually have to draw this longer. Okay, so that's the overall diagram. Now let's draw the diagrams for the individual objects. So for the treasure, we've got 80 kilogram object experiences what forces? Well, this is presumably happening on Earth, so I would expect to see a force of gravity, or weight, if that's what you prefer to call it. Force of gravity equals mass times g, so 80 times, I'll use 9.8 here for g. Whatever that value is, we can plug it into our calculator later. And then there's going to be some sort of normal force upward. We don't know if it's greater, less than, or equal to the gravitational force. I'm going to guess greater than. I'm going to be optimistic and assume that the pirates actually managed to pull this thing up. But it doesn't really matter. As long as you show that they're not the same. That's all we know for now. Actually, we don't even know that. They could be the same, but it's better to err on the side of them not being the same than to assume that they are. And that's it for the 80 kilogram treasure. The rest of the forces are going to be on our wooden plank. So let's draw a diagram of the wooden plank. That thing is going to be 20 kilograms. And the normal force exerted on the treasure is exerted by the plank, which means that the treasure is going to exert an equal normal force on the plank. So the plank is going to experience whatever normal force that the treasure is experiencing. These two have an action-reaction relationship there. This thing is also going to have a weight. That's an interaction between it and the Earth. So that's going to be, and I should actually draw this smaller. Hold on, let me scratch this out and I'll redraw it over here. Yeah, this should be smaller than this because, 20 versus 80. In fact, it should be 1/4 the size. So if you were doing this on the AP exam and they expected you to draw it to scale, they would take points off if you didn't get that right. So that's going to be force of gravity equals 20 times 9.8. And maybe I should have named these force of gravity treasure and force of gravity plank, but if I'm going to go ahead and write down their values anyway, then I don't think there's going to be any confusion as to which one is which. But that takes care of the two vertical forces acting on the plank. No friction is mentioned here. There's no reason to believe there's any friction going on. It's not rubbing against a wall, and we were told that the treasure doesn't wobble left or right, so there shouldn't be any sort of sideways friction between the treasure and plank either. So that just leaves the two tension forces. Force of tension right, which is not completely to the right. And force of tension left, which is something like that. And we were told it was equal to 800 newtons. Okay, there we go. Now we have our diagrams. Now let's break down our two angled forces into components. So force of tension right, I will draw a separate diagram for this. So force of tension right is going to have two components. It's going to have an upward component and a rightward component. And let's see, so if the 63-degree angle is touching the horizontal side, then that means the horizontal side goes with the cosine. Horizontal is adjacent to the 63 degrees in this case. So horizontal is cosine. So this is force tension right times cosine of 63. And this is then going to have to be, by process of elimination, force of tension right times sine of 63. Okay, that doesn't tell us much because we don't know what the tension in the right is, but we can work with this. And then force of tension left is going to break down similarly. 78 degrees is adjacent to the horizontal direction. So we're going to have force of tension left times cosine of 78, so that's 800 cosine of 78 degrees. And then for the vertical component, we're going to have 800 times sine of 78 degrees. Let me separate these from each other so that we don't accidentally read the wrong thing. Okay, and then just copy down the normal force and the weight. So normal force, currently unknown, and the weight, 20 times 9.8, would be 196. Force of gravity equals 196 newtons. Okay, so we don't know force of tension right, though we can actually solve for that. And we don't know normal force. Well, we can go ahead and solve for the force of tension right, because we do know something about the horizontal direction. We were told there is no sideways motion, there is no wobbling of the treasure, so the acceleration horizontal must be 0. Is this going to be another one of those days where I have to go through a box of tissues? I hope not. Okay, where was I? So, well, let's switch colors. So I know that these two forces must cancel out, and there's only one unknown between these two forces, so I can actually make this work out just fine. So net force horizontal, I guess this is going to be for the plank, but it's also true for the treasure itself on top of the plank. Net force in the horizontal direction is mass times acceleration in the horizontal direction, and the acceleration horizontal we can reasonably assume is 0, since we were told that the motion, it's not even an assumption, we were told that the motion was completely vertical. So that's gone, and that leaves us with forces to the right minus forces to the left, or you can do left minus right if you want the left to be the positive direction. It doesn't really matter. You end up with the same thing either way. But force of tension right times cosine of 63 minus, to the left I have 800 times cosine of 78. Okay, so this is supposed to be equal to 0, so if I add 800 cosine of 78 to both sides, I get 800 cosine of 78 degrees is equal to force of tension right times cosine of 63 degrees, whoops, 63, not 36. Divide by cosine of 63 and you've got your force of tension right. So let's go ahead and put that in our calculator and see what we get. 800 cosine 78, close parentheses, divided by cosine of 63. And I get 366.37. I get force of tension right equals 366.37 newtons. So, did I get it correctly? I forget what I said earlier about whether the 800 would be greater or less than, but clearly it's greater than force of tension right, which I guess does make sense because the cosine components need to cancel out, so the one with the bigger angle is going to have a smaller cosine. So yeah, even though it's got a larger value for the smaller cosine, it will balance out with a smaller force that has a larger cosine. Okay, yeah, that's making sense to me mathematically. It checks out. Doesn't hurt to double check your work like that. Okay, so that's part A answered. What is the force of tension in the Orange Pirate's cable? 366.37 newtons. Part B, what is the acceleration of the treasure? Will they get the treasure, or will it fall back into the ocean? Okay, so now we need to figure out the acceleration of the treasure, which is going to be a vertical acceleration. So let's go ahead and write our vertical net force equations. Net force Y of the treasure is going to be the mass of the treasure, which is 80 kilograms, times the acceleration of the treasure in Y. We don't know yet. I'm going to use up as positive and down as negative, so net force is also equal to the sum of the forces, so this must be equal to, I'm going to do forces up minus forces down, so 80 times 9.8. This I don't think I know off the top of my head. 784? 80 times 9.8. 784. Okay, at least I had to think about it a little bit. There might still be hope for me. I might not have fully drifted off into the realm of insanity. And that's as far as we go because we've got two unknowns. Well, wouldn't it be nice if we could come up with another equation that also has the same two unknowns? If I have two independent equations in the same two unknowns, I can solve them. Well, the hint did mention that the plank and the treasure move together, so they should each have the same acceleration. So acceleration y of the treasure is the same as the acceleration of the plank, so why not figure out net force y on the plank? If I do that, the plank is 20 kilograms, so 20 kilograms times the acceleration is the same ay. If they were different, then I would have called them ay plank and ay treasure. And that's going to be equal to forces up on the plank minus forces down on the plank. So forces up on the plank are 800 sine of 78. And force of tension right times sine of 63. Well, we solved earlier for force of tension right, so that's plus 366.37 times sine of 63. And that's forces up minus forces down. We've got the normal force. And we've also got the weight of the plank, which is 196 newtons. Okay, And one thing we could do to solve this system of equations is we could use substitution. We could rearrange this and say normal force equals 80 acceleration y plus 784, and then plug that in for the normal force over here and solve that way. And that's usually how we want to do things in physics. A lot of times when you're solving systems of equations, substitution is the go-to method. But in this case, and as we'll see a lot today, when you're dealing with systems of objects that move together, a lot of times the equations you write lend themselves to elimination. If I simply add these two equations to each other, it's already good to go for elimination because I've got one normal force here and minus one normal force there. They're going to cancel out. So let's go ahead and do that. Let's add these two equations to each other. So 80 acceleration y plus 20 acceleration y. That's going to be 100 acceleration y. Very nice number. Should be easy to divide our final result by 100. Just move the decimal 2 times. Normal force and minus normal force, those are going to cancel out. And then 800 sine of 78. I guess I'll go ahead and put that into my calculator. Actually, you know what? I'll copy it as is. And then I'll put it all in the calculator at the very end. 800 sine of 78. By the way, for those following along with their calculators, do not forget to make sure your calculator is in degree mode and not radian mode. Especially those of you who are learning physics along with your calculus or pre-calculus course, since those courses often have you switching to radians. Anyway, copied that, and now the negatives. Copy the minus 784 and the minus 196. And that's everything because the normal forces got eliminated. Okay, now put all of that into the calculator. So 800 sine 78 plus 366.37 sine of 63 minus 784 and minus 196. I'm getting 128.956. I'll just round it to 128.96. So I'm getting 128.96 equals 100 times the acceleration in y. And divide by 100, that's 1.2896. So acceleration in y, 1.2896. I'll just round that to about 1.29 meters per second squared. If my mass is in kilograms and my force is in newtons, then I should get my acceleration in meters per second squared. Okay, so that's part B answered. Part C said, what is the normal force on the treasure? So we can do this the easy way or the hard way. The easy way would be to use this first equation. The hard way would be to use the second one. The only reason that it's harder is just because it has more terms that need to be plugged in. So let's not. Let's just use the first equation. Add 784 to both sides. Plug in the acceleration we just calculated. And that's it. The other advantage of this first equation is that you don't have to worry about that negative. Saves you a couple of steps. Just a couple. Okay. I don't know how different this color looks from this other color. Dark blue versus navy blue. I don't think the difference is visible on the screen, not from what I saw when creating timestamps for the footage from last week. But maybe I'm just a bit colorblind, who knows. Anyway, first equation we have here says 80 times acceleration in y, which we now know is 1.29, is equal to normal force minus 784. Oh, come to think of it, I forgot to answer part of question B. So in addition to finding the acceleration, the question was, will they get the treasure or will it fall back into the ocean? Well, I got positive 1.29 meters per second squared, and I got that by using up as the positive direction. So a positive result when using up to be positive must mean that the acceleration is up. If for whatever reason you did the same math, but you took all of the downward forces to be positive while you took all the upward forces to be negative, then you would have gotten negative 1.29, and that would still mean up, because it would be opposite to the direction you called positive. If you called it down the positive direction, then you would get negative meaning up. So either way, the treasure moves up, which means it's not falling back into the ocean, which means, yes, the pirates do get their treasure anyway. 80 times 1.29, and add the 784 to the other side. 80 times 1.29 is 103.2. Add 784, and that should be almost 900. 887.2. I'm getting 887.2 newtons for the magnitude of the normal force between the plank and treasure. So that's the amount of force the plank exerts up on the treasure and the amount of normal force that the treasure exerts down on the plank. All right. That takes care of the problem we left off with last time. Now, how about we look at... Oh, I forgot to mute that desktop audio. Then I guess you guys must have heard an echo while I was doing the sound check earlier. Okay, well, that's a bit embarrassing, but I can live with it. Let's see, where was I? So next up we have, let me switch screens over here. So next up I want to introduce some more problems involving systems of objects, in this case involving the tension force. So we've talked about the tension force before. It's always a pull, it's never a push. It always is parallel to the rope, and it only exists when the rope is pulled taut, not when the rope goes slack. So you want the rope to be straightened out and actually tensed up. So we've got, number one says 3 objects are being pulled along. Yeah, all of these are frictionless surfaces. So I already have the solutions video for this one. So rather than do this, I'm going to pull one from my book that's similar to it, just so we have something different for those who already did this in the homework. Let's see what we've got in my book. That's a little too far. Here's a nice one. So let me flip the page over. And the book presents us with the following problem. It says, assume that the 3 blocks portrayed in the figure, and I'll go ahead and draw the figure for you. Is my camera screen on? Yes, it is. Okay. Don't want to make the mistake from, what was it, 2 weeks ago, where I was drawing and talking while the screen was showing whatever I had up, the web page, the PDF, or whatever it was. So we have the floor, and then we've got a 1 kilogram object. 1 kilogram. Let's add serifs to that 1 so that it's not mistaken for an L or something like that. Then next to it is a 2 kilogram object. And next to that is a 3 kilogram object. Well, not directly next to it, but up here is a 3 kilogram object. And it shows a rope connecting the 1 kilogram object to the 3 kilogram object. So there's a rope there. And it shows, let's see, so assume that the 3 blocks portrayed in the figure move on a frictionless surface, so frictionless, and that a 42 Newton force acts as shown on the 3 kilogram block, so they have a force drawn. I guess we'll call this an applied force, force applied of 42 newtons. Maybe this applied force is actually a tension force and they're just pulling the 3 kilogram block by another rope that we don't see, or maybe they're just pulling it with their hands, in which case they would be using the static friction force. If you're dragging something like this, then what you're actually doing is you're using static friction. You're trying to make sure that the acceleration of, in this case, I guess I have a calculator in my hand, you're trying to make sure that the acceleration of the object in your hand is the same as the acceleration of your hand itself. So as your hand moves, the calculator moves with it. That's the static friction force at work. So that could also be what the applied force is. Or maybe there's some invisible person that we don't see who is putting their hand behind this 3 kilogram block and pushing it, in which case it would be a normal force. I know I rambled about that before, but it doesn't hurt to reiterate that applied force is not actually a real type of force. It's usually going to be some sort of tension, friction, or normal force. Anyway, the problem is asking us to determine part A, the acceleration given to this system, part B, the tension in the cord connecting the 3 kilogram and the 1 kilogram blocks, and part C, the force exerted by the 1 kilogram block on the 2 kilogram block. Okay, so we have to make some assumptions here, which are common sense assumptions. I don't think anybody is going to be surprised by this, but if I were to set up blocks in this way and I start dragging this 3 kilogram block, then I would expect all 3 blocks to move in lockstep with each other. I think that's a reasonable assumption. So whatever velocity the 3 kilogram block has, these 2 blocks move with the same velocity, and if this 3 kilogram block speeds up, then these 2 blocks will also speed up right behind it. So the system starts with the same velocity, which I guess we can assume is from rest, although it's not going to matter even if it's not from rest, and they have, most importantly, the same acceleration. So acceleration of block 1 equals acceleration of block 2 equals acceleration of block 3. Usually I will refer to this shared acceleration as the acceleration of the system, a sys. Without this assumption, you'd be stuck because you would have these 3 unknown accelerations, but if they all have the same value, then that reduces you from having 3 unknowns to just 1 unknown acceleration. So if you're encountering a problem like this and you're having way too many unknowns and you can't come up with enough equations to resolve all that, then chances are you were expected to make some sort of simplifying assumption. So double check your understanding of the problem and see if there's a relationship between your unknowns that might reduce them into fewer unknowns. Okay, so part A was determine the acceleration of the system. Well, we've got 3 objects, so guess what we need? 3 diagrams. 3 objects require 3 diagrams. So I guess I'll declare object 1 to be the 1 kilogram and I'll just read them off from left to right. So object 1, 1 kilogram object, or you could call its mass M1 if you prefer. It's going to have, oh goodness. It's going to have what force is acting on it? Well, it's on Earth, so it must have some sort of weight to it. Force of gravity, I guess we'll call it force of gravity 1. Equals m1g equals 1 times 9.8. It's going to have some normal force because it's in contact with the surface, and the normal force is always perpendicular to and away from whatever it's touching. It's also connected to a rope on the right-hand side, so there's going to be a force of tension. And the force of tension is always parallel to the rope and towards. And the rope, of course, doesn't have to be a rope. It can be a chain or something similar. It can be rope-like. And it's also touching another thing. It's touching the 2 kilogram block, which means there's another normal force. So in fact, I'm going to call this normal force ground to distinguish it from this other normal force. I'm going to call this normal force block. Whoops, I meant to write an F there. Force, that's an F. Force, normal, blocks. Normal force between the 2 touching blocks. And that's going to be to the left because it has to be away from the thing that it's touching. Perpendicular to and away from the vertical surface of contact between the 2 of them. And I think that is it. They did say that the surface is frictionless, so there shouldn't be any friction here. If there was, it would have to be to the left because the only reasonable assumption here is that the 1 kilogram block and actually the whole system would accelerate to the right. There's no scenario in which you start with this setup and you tug on it to the right and it starts moving to the left unless it was already moving left to begin with, which is not something we should assume because otherwise the problem would have told us or would have given us some other way of deducing that that was the case. So we are done with diagramming block 1. Block 2, the 2 kilogram block. Well, the 2 kilogram block is on Earth, so force of gravity 2 is equal to 2 times 9.8. This thing also experiences a normal force with the ground. It's not going to be the same as this, so I guess I should call this normal force ground 1. And I'll call this normal force ground 2. I don't like how I named this, but it's fine. And then what else? Well, if it's accelerating to the right, something must be pushing it to the right, and that would be the 1 kilogram block. Right? It pushes the 1 kilogram block backwards, and the 1 kilogram block pushes it forwards, forward being to the right in this case. So there's a normal force coming from its left side towards the right, because its left side is in contact with the 1 kilogram block. So that's normal force blocks. These are action and reaction. These are going to have the same magnitude. And that's it. Nothing else needs to be drawn here. I don't see any springs. The 2 kilogram block is not connected to any ropes, so no tension forces either. And the surface is frictionless, so no friction forces. Okay, off to the third object. And don't worry, we will get to tougher problems. If some of you are rolling your eyes at this and thinking it's too easy, we're building up to tougher and tougher problems. We'll see those eventually. But we gotta start with the basics. If we don't master the basics, we have no business doing the tougher problems. A lot of people want to rush to the tougher problems, and that's where they get stuck, because they haven't truly mastered the basics yet. So 3 kilogram block, we've got, of course, its weight. So force of gravity 3. I tried to draw these somewhat to scale, or at the very least, I drew them so at the very least we can tell that force of gravity 2 is greater than 1, and force of gravity 3 is greater than both of those. So that's 3 times 9.8. And then we've got normal force ground 3, of course. And then we have, what else? The force applied, of course. Force applied is 42 newtons. Actually, should be even bigger than this, come to think of it, because this is definitely less than 42. So I guess I just wasted my efforts trying to draw things somewhat to scale. But that's okay, because the problem never asked that of me. Like I said before, never assume that my drawings are to scale unless I say so. And last but not least, we've got the tension force. Since it's from the same rope, it should just be the reaction to the tension force on block 1. So yeah, blocks 3 and 1 should have an action-reaction relationship between them. And yeah, that's it. No friction. And it's not touching anything other than the ground, so that's the only normal force there. And no springs. We're good to go. Now that I have three diagrams for my 3 objects, we can write 3 sets of Newton's second law equations. I say 3 sets of equations because you need to write it for the x and for the y. We could actually pass on the y in this case, but I'll write it out anyway. So net force for object 1 in the y direction is going to be, well, we know the acceleration in the y direction is going to have to be 0. So you've got 1 kilogram times an acceleration of 0 equals normal force ground 1 minus force of gravity downwards is 9.8. And that would allow you to solve for normal force ground 1, which isn't really useful here because we don't need it for anything. We were not asked to calculate it. But you could do it if you wanted to. And if there was friction in this problem, then we would actually need this, specifically if the friction was between the blocks and the ground. We would need to know what the normal force between the blocks and the ground would be in order to calculate that friction. So calculating normal force isn't completely useless. It's just, in this case, not necessary. And we can do similar for objects 2 and 3. So we can do net force of object 2 in the y direction. I'm just going to blitz through this. Is 2 kilograms times 0 acceleration in the vertical equals normal force ground 2 minus, in this case, 2 times 9.8 is 19.6. Okay, and net force 3 for the y direction is 3 kilograms times 0 equals normal force between the ground and block 3 minus, what's that going to be, 28.4? No, wait, 29.4. And yeah, so that just tells you what the 3 normal forces are. They end up being equal in magnitude to the gravitational force on each block. No surprise there, given that there are no other vertical forces to counter gravity. It all falls on normal force to keep these boxes from burrowing a hole into the ground. Okay, what about the x direction? This is where the interesting stuff happens for this problem. So net force on block 1 in the x direction equals the mass, 1 kilogram, times the acceleration in x. We are going to call that the acceleration of the system. And I'm using right as the positive direction here. So I guess I'll just say positive direction to the right. It's going to be important to get into the habit of doing this later. I think next week is when we will introduce pulleys. And for pulleys, you're not going to be using the conventional positive directions all the time unless you want to really inconvenience yourself. So getting into the habit of predefining your positive direction there is going to be crucial. Anyway, we've got 1 times acceleration of the system equals forces to the right. So to the right I've got force of tension. And that's it. Minus forces to the left, I've got the normal force between blocks 1 and 2, normal force blocks. And that's it. Net force on block 2 in the x direction equals 2 kilograms times the acceleration of block 2 is the same acceleration as all of the blocks, a system, equals forces to the right minus forces to the left. All I have is one force to the right, normal force blocks. Okay, great, but I can't do anything with this because I've got two unknowns. And I can't use it with this equation because this equation has three unknowns, so I need a third equation. Net force on block 3 in the x direction is 3 times the acceleration of the system. Equals, let's see, forces to the right minus forces to the left, force applied of 42 newtons minus force to the left is the force of tension. Okay, so here we've got three equations and how many unknowns? The acceleration of the system is unknown. The tension force is unknown. These are both the same tension force, so they count as just one unknown. And the normal force between the blocks is unknown. So three equations in three unknowns, and these three equations should be independent of each other. I didn't calculate one of them by just taking another one and multiplying it by 2 or something like that. There is no reason to believe that any of these equations are derived from the other two. So yeah, these equations should be independent, which means we should be able to solve them for our three unknowns. What color do I want here? Let's go back to you. Oh, goodness. Maybe I should have made some warm tea before this. So what I can do is, well, I hinted at it earlier. When you're dealing with systems of objects, a lot of times you will notice that elimination is very convenient to do. If I were to simply add these three equations to each other, I can see that force of tension would cancel with force of tension, and the normal force between the blocks would also cancel out. So let's do that. 1A system plus 2A plus 3A equals 6A system. So that's the left-hand side, all added up, equals force of tension minus normal force blocks plus normal force blocks. So normal force is eliminated. Plus 42 minus force of tension is eliminated. I'll write it all out. So force tension minus normal force blocks, that's what we get from the first equation, plus normal force blocks these get eliminated. And then from the third equation, we add 42 minus tension force. Oh, well, we've got tension force and minus tension force canceled out. So all that's left is 42. And 42 divided by 6, acceleration of the system is 42 divided by 6 is 7 meters per second squared, which is actually quite a lot. Considering how big a meter is. The number looks small, but that's actually quite fast if you were to see it in real life. That would be, well, let me see. So in 3 seconds, you would be moving at 21 meters per second. How fast is that? In just 3 seconds, let me just use the Google calculator for this. So 21 meters per second to miles per hour. That is 46.9, so almost 47 miles per hour in just 3 seconds. Yeah, that's quite a lot. Okay. Now, where did I want to go from here? Part B said, calculate the tension in the cord connecting the 3 kilogram and 1 kilogram blocks, so that's going to be next. Well, now that we know one of our 3 unknowns, the rest should be easy. So if we're looking for the tension, then it looks like we want to use this third equation over here because it involves the tension we want to solve for and the acceleration that we just calculated. If we use the first equation, we would still have the unknown normal force between the blocks, and that would be more of a hassle, although it would still be doable, because if you really wanted to, you could just combine the first 2 equations. That would eliminate the normal force between the blocks, and then you would say 3 acceleration of the system equals the tension force, which, well, now that I've already done it, is actually easier. If I add the first 2 equations, normal force blocks cancels out. 1 plus 2 equals 3. A system equals the force of tension. Plug in 7. Force of tension is equal to 21 newtons. Force of tension would then be equal to 21 newtons. Well, let's see if it still works if we calculate it using just the third equation alone. So if I do third equation by itself, I would have 3 times the acceleration of the system, which we got to be 7, is equal to 42 minus tension force. Subtract 42 on both sides. 21 minus 42 is negative 21. If negative 21 equals negative force of tension, then would you look at that same result? Force of tension equals 21 newtons. So either way, whatever is easier for you. I mean, one of them is easier in the sense that you don't have to, get rid of any coefficients in front of the tension force. But the trade-off is, unlike the other one, you do have to combine 2 equations, whereas for the other one, you've got 1 equation to work with. So it'll depend on the situation whether or not that trade-off is worth it. So, just you'll develop your own sense for whatever it is that you prefer. But it's good to know more than one way to approach the problem, because that gives you more than one way to double check your work and potentially catch mistakes. So that is part B. Part C says find the force exerted by the 1 kilogram block on the 2 kilogram block, which of course is the same as the force exerted by the 2 kilograms on the 1. It's just this normal force between the blocks, and it looks like our easiest option is to just use the second equation for the horizontal net force. 2 times 7 equals normal force blocks. I'll do it right here. 2 times 7 equals normal force blocks. I mean, if we're being honest, I didn't even have to write it out. I think you can all do 2 times 7 in your heads. But, if this was on the AP exam, you would want to write it out. You wouldn't just want to write down 14. And there we go. So we've got a 14 Newton force between the blocks. Okay, so that's the problem itself done, but now let's do the thing that I like to do, the thing that I encourage you guys to do. I've mentioned this before, but what you should be doing when studying isn't just doing the problems, but also reflecting on the problems and asking yourself what you learned from them. And this problem gives us a little bit of insight into how to think about systems of objects. Come to think of it, the previous problem did too, but I didn't really point it out. So both this current problem and the previous one, and I forget which problem it was from last time that was similar, you could get away with treating the system of objects as a single object whose mass is the same as the total of the masses of the individual parts. You would find, if you did the math for this pirate and treasure problem, you would find that if you drew, and I would encourage you to do this on your own time, I'm just going to give you a summary here, but if you took 80 kilograms plus 20 kilograms, if you treated this as a 100 kilogram object and redrew its diagram showing only the external forces, by external forces I mean the forces that come from outside of the system, not forces that the parts of the system exert on each other. So in this case, all the forces except for this normal force. That normal force is exerted by one part of the system on the other in each of these diagrams. In this case, it's exerted by the 20 kilogram plank onto the 80 kilogram treasure. In this case, it's from the 80 kilogram treasure onto the 20 kilogram plank. And those I would call internal forces because they are forces that exist inside of your system, the system being defined as just these two objects. If you eliminate the internal forces, then what you're left with is a force diagram that looks something like this. Force of tension right, force of tension left, and a total force of gravity equal to 100 G. And if you did your math with just that, you would get an equivalent result. You can actually see that in, let's see, in here. If I were to, well, actually I did do it right over here. When I added the two equations to each other, I got this expression. And what's this expression? It's the upward components of the two tension forces minus 100 G. This would be equal to 980. Minus 784 and minus 196 should be minus 980, which is 100 times 9.8, so that's 100 G. So yeah, this equation implies this diagram, or rather, well, this diagram with the vertical components drawn for the tension forces. And for the horizontal components, this diagram still works because you would still get, where was it? You would still get this. You would still get force of tension right, cosine of 63, canceling out with 800 cosine of 78. So yeah, this would be your equivalent diagram if you were to condense it to a single object. Okay, what about over here? What about over here? So we've got ourselves 42 newtons acting on a total of 6 kilograms. So if I were to redraw this, this is equivalent to a single 6 kilogram object being pulled to the right with a force of 42 newtons. If I did that, I would get the same acceleration, 7 meters per second squared. So I would get that same acceleration, and my internal forces disappear. So internal forces in this case were the tension force. That was a force exerted from one block onto the other and vice versa. And the normal force between the 1 and 2 kilogram blocks also disappears. So all that's left is the applied force and the ground normal force ground. and the weight. And for the weight and ground normal force, they would just be the sum of these three ground normal forces would give you the total ground normal force on that system. And if I were to add these, 1 times 9.8 plus 2 times 9.8 plus 3 times 9.8, oh, would you look at that? It's 6 times 9.8, the weight of a 6 kilogram object. So yeah, it checks out. And of course, then it makes sense why these normal force ground 1 and 2 and 3, which are going to be equal to 9.8, 19.6, and 29.4, also add up to whatever the equivalent of 6 times 9.8 is. Whatever that value is. What is it? 58.8, I think? 9.8 times 6. 58.8. I hate that I know this. I hate that I have this gut instinct that tells me, yeah, that number sounds right. We will see situations where, how do I want to word this? We will see situations where it's not as simple as just smushing the objects together and drawing whatever forces are still on the outside. There are going to be situations, especially when it comes to pulleys, where it complicates things. So don't get too excited about condensing everything into a single object just yet. Use it as a way to check your work. Use it as a way to quickly just get a feel for what kinds of numbers you should be expecting to see. But I would prioritize making sure that you know how to do things like this, how to do things the long and hard way from base principles, because honestly, once you practice this enough, I know I took a while with it, but that's because I'm pausing and going slow in order to explain things as I go. If I were taking a test, I would blow through this in probably 2.5 minutes at most for this whole problem, if even that. But once you practice this enough, you should be able to do similar. You should be able to get through this fairly quickly without even having to rush yourself. If you're rushing, then you're doing it wrong. If you're rushing, then you haven't practiced enough, or maybe you haven't practiced correctly. Maybe you haven't focused on the right things when practicing. I don't know how many of you have seen my video about, what was it titled? I think it was titled, How Long Should I Study? This Might Be a Stupid Question, or something like that. I would recommend that you go and watch that video because it has my honest advice on how you should approach studying. But now I'm going off on all sorts of tangents. I need to get back to what I wanted to say about this problem. So let's try and pick this apart a little bit and see how nicely everything just works when you take this big picture perspective. So we've got 42 newtons of applied force, and if you look at the internal forces and you see what they're doing, what they're really doing is that they're just evenly distributing this overall force. This overall 42 newton force is being evenly distributed by the internal forces across all of the different masses within the system. So the tension force being 21 newtons, basically takes half of the 42 newtons away from the 3 kilograms. The 3 kilograms is left with only 21 to the right. And that makes sense because 3 kilograms is half of the mass of the system. If you have half the mass of the system, you get half of the net force on the system. You get 21 newtons. Otherwise, some parts of your system would be accelerating at a higher rate than others. If the force is not evenly distributed across the mass, then this is no longer true. This over here, this assumption, wouldn't have been true. For this to be true, the force has to be evenly distributed about the mass, the net force, to be specific. So, yeah, the tension takes away 21 newtons of force, takes away half of the net force, leaving half the mass with only half of that applied force. The other half goes to, well, both of these, really. Sure, it's going directly to the 1 kilogram block, but the 21 newtons doesn't all go to the 1 kilogram block because there's this, where did I put it? There's the normal force between the blocks, which does a similar thing. The normal force between the blocks pushes left with a force of 14 on the 1 kilogram block and pushes right with a force of 14 on the 2 kilogram block. What's that doing? Well, it's taking the 21 that would have all gone to the 1 kilograms and takes away 14 from it. This 21 newtons needs to be distributed over 3 kilograms. So this 1 kilogram, since it's only 1/3 of the 3, it should only be getting 1/3 of the 21, so the other 2/3, the 14 newtons, needs to be taken away from it. And that's what the normal force is doing. And it's redistributing it to the other 2/3 of this 3 kilogram section of the total mass. Hopefully that made some semblance of sense. This isn't really something that you absolutely need to know for the AP exam, but I would encourage you to think about it anyway, because it'll just help you deepen your understanding and it'll give you some sort of competitive advantage. And you shouldn't be saying no to competitive advantages. I mean, even if you take the competitive aspect out of it. You shouldn't be saying no to anything that can help deepen your understanding of just the laws of nature and how the world works. Even outside of school, you might one day find that this understanding might come in handy, even if you don't necessarily bring out a paper and pencil and start whipping out calculations. Just the intuition of this might help you in some sort of situation that you find yourself in one day. But yeah, I will leave you to kind of chew on that and let it digest in your head. Or rather, heads plural, because there's more than one of you watching. But you get what I mean. Okay, so where do we want to go next? What do I want to do next? Well, I've got another problem here that might be worth looking at. Let me see what I have. In this book. Don't want to do those yet. I guess... Okay, we're going to need to do a systems problem with friction at some point. But also I would like to do a vertical problem, so let's do a vertical problem. And again, I'm just going to take one from my book. There is a vertical problem in the actual homework PDF right here. This one is for two objects that are hanging still from a ceiling, and you saw the solutions for that if you just went to the course plan. Again, the link is in the description. Open up Force, just in case you're new here. Follow the link in the description and you'll be taken to this page. And if you scroll down to the Force section, I'm looking at forces on systems of objects. There's the solutions for that linked in an unlisted video. So if you open that, we get to here, and yeah, this over here is just for two objects hanging still from a ceiling. I want to do something similar, but this time instead of hanging still, there's going to be some sort of acceleration. So in my book, I have the following question. And actually, I think I want to change one of the masses. So they have an elevator. Oh, actually, I could assign some sort of mass to the elevator and make this, well, okay, I'll go easy on you guys and not torture you with that for now. But let's say we've got these two objects over here connected by ropes, and it says in my book that they're both 10 kilograms, but I'm going to modify the problem and say that this object is 10 kilograms while this one is 15 kilograms. And it says that this elevator accelerates upward. Acceleration in the y direction, acceleration y, is equal to 2 meters per second squared. And it says find the tension in each rope. Find the tension in each rope. Well, at least in this problem, the diagrams are simpler than the previous problem, because there is only one dimension to worry about. There is no set of net force x equations to write. And also, we've got two objects as opposed to three. But yeah, we've got two ropes, so they're going to have two tensions in them. I'm going to call this rope 1. The top rope is going to be rope 1, while the rope between the 10 and 15 kilograms will be rope 2. So we need to find, let me draw the diagrams first. So for the 10 kilogram object, I need to find well, we've got force of tension 1 upwards and force of tension 2 downward, and also the weight downward. So I guess I'll call that M1G. I'm going to say that the 10 kilogram object is object 1. For the 15 kilogram object, I'm going to do similar, so $15 kilogram object, I'm going to have pulling up on it is force of tension 2. It's connected to the second rope after all, so force of tension 2. And pulling down on it, I guess I didn't draw these to scale because tension 2 should be greater than what I'm about to draw. This is why I tell you not to assume that my drawings are to scale. This is going to be M2G. And I guess for simplicity's sake, I will use G equals 10 for this one. I'll use G equals 10 meters per second squared, just to make the math go by a little bit quicker. This is what I'm going to use. I don't know why I circled it like that. Makes it look like it's some sort of answer. Didn't mean to do that. Didn't mean to imply that. But anyway, so two objects, two diagrams, two sets of net force equations, except, well, they're not sets because I don't need to do the x's. Net force x is 0 and there are no forces, so yeah, net force x for object 1 and 2 we can skip. So net force x for object 1 and net force x for object 2. Those are 0 and nothing interesting happens. We can ignore that. Net force y for each object. This is where the interesting stuff happens. net force y for object 1 and net force y for object 2, we have net force y for object 1. We've got forces up. Oh, wait. First of all, mass of object 1 times acceleration of object 1 is just going to be the acceleration of 2 meters per second squared, this AY. I'll call it A system. I'll call it A system. And over here, yeah, there, A sys. Is equal to forces up minus forces down. I'm using up as positive because, well, they gave a positive value to an upward acceleration, so I guess the positive direction was decided for us in this case. Although you could still change it if you wanted to. If you really want down to be positive, you would just have to remember to add a negative sign onto this in order for all the math to work out correctly. I don't know why you would do that, but okay. So forces up, force of tension 1, minus forces down, that would be force of tension 2, and also M1G. And over here, for net force y on object 2, it's mass 2 times the acceleration of the system, equals forces up, force of tension 2, minus forces down, M2G. Okay, if I add these equations to each other, that's the pattern. M1 plus M2 times the acceleration of the system equals, let's see, tension 1 does not cancel with anything, so that's coming down. Minus tension 2 and plus tension 2, that's gone. And then minus M1G and minus M2G. So minus M1G and minus M2G. I can factor out the minus G and have minus M1 plus M2 times G. Okay, if we write it this way, we can see more of what I was saying about this whole systems thinking, where if I were to draw an equivalent object that is 25 kilograms, 25 kilograms, this is just M1 plus M2. This is the mass of the system. And then if I were to draw, let's see, tension 1 would just be an external force acting on, well, let me draw a dotted line outlining where our system begins and ends. Right there. That is our system. So it starts right at the bottom of rope 1. So yeah, force of tension 1 upward, and we've got the mass of our system times G, M system times G, and that would be it. If we were to replace these two blocks with a single 25 kilogram block, this is what the diagram would look like, and if you look at the math, that actually checks out. Net force Y on the system is equal to the mass of the system times the acceleration of the system equals forces up on the system minus forces down on the system. So yeah, it's consistent with the math. As long as you can prove that it works out mathematically, only then, once you fully understand the connection between this and this, only then can you start taking these shortcuts. But until then, please just do it the long and hard way. Wait for that understanding to really just kind of crystallize in your mind before you start taking shortcuts, because if you become over-reliant on shortcuts, you're not going to learn. Anyway, if I go ahead and plug in my numbers, I'm going to get 25 times the acceleration is 2 equals force of tension 1 minus 25 times G, 25 times, I'm using 10 for G here, so that's minus 250. So that's 100. Or no, not 100. What am I saying? 25 times 2 is 50. 50, and then plus 250, that's going to be 300 equals force of tension 1, specifically 300 newtons. Do not forget the units. So that's one of our answers. The other one was to find the tension in rope 2. Now that we know tension 1, we can... Oh, actually, we can solve for tension 2 without needing to know tension 1 at all. We can just use the second equation over here. So let me switch colors. What do I want to use? Let's do green. I'll do it over here. So mass 2, which is 15 kilograms, times the acceleration of the system is positive 2, equals force of tension 2 minus m2g minus 15 times 10. Okay, 15 times 2 is 30, and then 30, add 150 to both sides, that's 180 newtons for force of tension 2. Okay, so 300 and 180. Now let's go ahead and do that sort of proportion check that I alluded to over here. So the total external force on these objects, well, we know it's evenly distributed as far as the gravitational force is concerned. I know that the total mass of the system, I know that the 25G is evenly distributed over the 10 and 15 kilograms because the 10 gets 10G and the 15 gets 15G. That I don't need to check. But what about this external tension 1? What about this force of tension 1, which was 300 newtons? Is that evenly distributed over the 10 and 15 kilograms? The 10 is 2/5 of 10 plus 15. It's 2/5 of the 25 kilogram total. So if I have 300 newtons and I have 180 here, that would leave 120 and 180. Yeah, there's a 2 to 3 ratio between those. 120 is 2/5 of 300, while 180 is 3/5 of 300. You can slow down and bring out your calculator to check that math if you need to. But I would hope you would eventually get to a level where you can see that without the need for a calculator. But if I were to draw, well, actually I have the diagrams right here. So tension 1 is 300 minus tension 2 is 180, so 300 up, 180 down is 120 up, versus over here you've got 180 up. Yeah, makes sense. So this one has 10 kilograms, needs 100 and, or no, where was it? 300 minus 180. The net tension, I guess you could say. This is a weird concept, but net tension on the 10 kilogram object is 120 newtons upward. So 120 up on 10 kilograms for 15 kilograms, 1.5 times as much mass would need 1.5 times as much tension. 1.5 times 120 is indeed 180. 120 plus half of 120, which is 60, gives you another 180. So now we've checked it in, I don't know, 3-4 different ways. It's all checking out. If that all just kind of went over your head, like I said before, you don't need to know this for the AP exam, but I would encourage you to just kind of reflect on this over the week and see if you can start developing a sense of intuition for it. Because if nothing else, it gives you one more way to check your work and make sure that you're not, miscalculating things. One way to get better at catching mistakes is to be able to recognize when numbers should be proportional to other numbers you already have. That might be what saves you when you overestimate or underestimate something. That could be the telltale sign that alerts you to something being wrong. Okay. Now, what do we want to do? Are there any other problems of this type in my book, particularly ones that involve friction? I mean, I've seen some that also involve pulleys and ramps, but we're not ready to go there yet. I think I may have done this in one of my review videos, so sorry for those of you who have looked around through my older review content and seen this one before. But it says, consider a large truck carrying a heavy load. I hope this is the problem that I think it is. Consider a large truck carrying a heavy load such as steel beams. A significant hazard for the driver is that the load may slide forward, crushing the cab if the truck stops suddenly in an accident or even in braking. Assume, for example, that a 10,000 kilogram load sits on the flatbed of a 20,000 kilogram truck moving at 12 meters per second. Assume the load is not tied down to the truck and has a coefficient of static friction of 0.5 with the truck bed. Calculate the minimum stopping distance for which the load will not slide forward relative to the truck, and is any piece of data unnecessary for the solution? I can't tell off the top of my head if this is actually the right problem, but we will see. So, I'll copy the numbers over in a minute, but we have ourselves our big truck. And I'm not going to draw all 18 wheels. 2 pairs of wheels will do for now. Oh, well, I guess we're going to need wheels there too. And they said it's a 20,000 kilogram truck. 20,000 kilogram truck that has a 10,000 kilogram load. I'm drawing it on top of the truck. Well, they did say it would be on top. I don't know what. Well, I guess it's not really an 18-wheeler. But no, wait, it would have to be. It's a 20,000 kilogram truck. A normal pickup truck is just a little over 2,000 kilograms. Well, maybe not just a little over, but in the ballpark of like 2,000 to 4,000 kilograms, right? I mean, I'm not the person that you should be trusting for knowing the masses of actual cars. But I would think it's somewhere on the order of 1,000. So yeah, this would actually have to... Why on earth wouldn't they just put it inside the truck in that case? Who knows? I'm not going to question it any further. Let's get back to the physics. So they said there's a 10,000 kilogram load that sits on the Flatbed. Oh, okay. So I guess it's one of those trailer trucks. Okay. I think I get it. I think it's one of those. I'm not going to redraw the whole diagram, but I think it's one of those, like, trailer trucks that's like tugging along this big cart. Yeah, something like that is what it should actually be. But anyway, we'll just go with this drawing because we've already drawn it. So it says assume that it's moving at 12 meters per second, so leave that alone. This thing is initially moving, v initial is 12 meters per second. Assume the load is not tied down to the truck and has a coefficient of static friction of 0.5. So there's going to be static friction between the truck and the load. And the coefficient of static friction, they didn't mention if it was maximum, but that's what we're going to assume. It would be too optimistic to assume the opposite. It would be too optimistic to assume that the maximum static friction coefficient is any higher than what they told us. In general, when you want to make assumptions for your physics problems, try to go towards the more pessimistic assumptions, because the optimistic assumptions can get so optimistic that there isn't even a problem to solve anymore. That's your FYI on, I guess, mind reading what the writers of the problem were thinking of having you do. That's just a little sort of problem writer psychology for you. Problem writer psychology. That has to be a new term. Well, if it's not, you heard it here first anyway. Calculate the minimum stopping distance for which the load will not slide forward relative to the truck, and then is there any piece of data unnecessary for the solution? Those are the two questions. So A, delta x stopping, and then part B, which data, if any, is unnecessary. This which data is unnecessary question is actually a very good one to have this early in the course, because it will help you adopt a certain mindset for physics. A lot of times in physics, you're going to think that you need some information that you don't actually need, and a lot of students will kind of start panicking and not even attempt to solve a problem because they think they don't have enough info. And one way to get over that fear is to get into the habit of kind of doing what I did back over here, where I didn't plug in anything until the very end. Try not to substitute your values too early. I know I kind of flip-flop between plugging things in ahead of time versus not, but that's because I already know where things are going. But if it's your first time doing a sort of a certain type of problem, then it might not be a bad idea to just leave things kind of like what I did over here, actually. Not plugging in the numbers, because that can help you detect patterns, that can help you find things like what we did here that helped us kind of clarify what this system diagram even meant. And also, it will let you spot when certain pieces of data get canceled out and eliminated, as we will see over here. So I'm going to call this MT for the mass of the truck, and I'm going to call the 10,000 kilograms ML for mass of the load, because I get the feeling one or both of those might cancel out. And then I guess start diagramming, because I'm not sure where to go next, at least not immediately. So we've got, I guess, for the 10,000 kilogram load, I'm just gonna write its mass as ml. We have what forces are acting on it. Well, we've got a force downward due to gravity, so that's ml times g. And then we've got, since it's touching a surface underneath it, there's got to be a normal force, so that's normal force between the truck and the load. And there's going to be a friction force. And which direction is the static friction force? Static friction force tries to keep the relative velocity between the truck and the load equal to 0. If the truck is accelerating forward, then the static friction will try to accelerate the load forward. And if the truck is accelerating backward, then the static friction will try to accelerate the load backward. In this case, we said that the truck is going to be stopping. So in the absence of friction, what would happen is the truck would stop, the load would continue, it would be carried forward by its inertia, and then it would slide and potentially just tip over and fall right on the driver's head, which would not be good. So the static friction is going to try and prevent that, which means that the static friction is going to have to be to the left in this case. It doesn't matter that the truck is moving to the right. What matters is it's going to be accelerating to the left. And so static friction is going to make the load accelerate to the left with it so that it keeps pace. Force, friction, static is going to be to the left. At least it's going to be to the left on the actual load. For the truck, it's a different story. Yep, it's Newton's third law, action and reaction. I'm just going to redraw the truck as a block for the sake of speed. So here you've got the truck. We've got the mass of the truck times g, of course, since this truck is presumably on Earth. We've got, I guess I'm going to call this normal force truck, normal force between the truck and the load, while here I'm going to draw an upward normal force. This is the normal force between the truck and the ground. I'm going to call this normal force with the ground. And of course there's also the reaction to normal force truck, whatever normal force the truck exerted up on the load exerts an equal amount down on the truck. So that's normal force truck. And the static friction is also exerted by the truck on the load, so the load is going to exert an equal and opposite static friction on the truck. So there's force of friction static. It actually pushes forward on the truck. It actually tries to drag the truck forward, which does make sense when you think about it. If the truck hits the brake all of a sudden, then if there's not enough friction, what will happen is that the load will drag itself over to the right, and of course, because it's in contact with the truck, it will partially drag the truck with it. The truck has more mass, so it's not going to easily get dragged, but at the very least, it would experience some resistance to its attempt at braking. That would be the interpretation there. Now back to this diagram. Was there anything else? Normal force down from the load. We drew gravity, normal force from the ground, friction from the truck. There's also going to be something that's causing it to decelerate. This truck has to have a net force to the left in order to slow down, in order to accelerate to the left. So there's one more force. You could call it an applied force from the brakes. You could also call it the friction force from the road. I'll just call it force of friction road. I'll call it force of friction road, which I guess would be a kinetic friction, since the truck is moving relative to the road. The road and truck don't have matching velocities, so that would be a kinetic friction and not a static friction. And we can't actually calculate this because we don't know the coefficient of friction between the truck and the road, nor do we know the other thing that it could be called, the force that the brakes exert on the truck. So we don't know that information, and we probably are not going to need it. I mean, they're asking this part B for a reason. But otherwise, our diagrams appear to be complete. Let me do one quick check and make sure I'm not forgetting anything. So both have to accelerate left. That one has a net force to the left due to static friction. There's nothing that's going to push it to the right. It starts off moving right, but that doesn't mean there's a force pushing it right. That's just inertia. Normal force and weight, and yeah, that should be everything there. Over here, normal force reaction, friction force reaction, some sort of decelerating force. Yeah, we're good to go. Okay. Now, they were asking, again, assume the load is not tied down to the truck and has a coefficient of static friction of 0.5 with the truck bed. Calculate the minimum stopping distance for which the load will not slide forward relative to the truck. Okay. So if I go ahead and write my net force equation for the load, let's see what we can do there. I'm going to need vertical and horizontal, so I guess we're going to continue this on the back side of this page. But let's see how much I can squeeze in here. Net force Y on the load is going to be equal to the mass of the load times the acceleration in Y should be 0, equals forces up, so that's normal force truck, minus forces down, that would be mass of the load times G. So that tells me then that since normal force minus weight has to be 0 for the load, that the normal force is equal to the weight in this case. Yes, I'm probably going to stress that every time we have this situation, because I don't want people to adopt the false belief that normal force is always equal to mg. So, actually, I'm not even gonna use my calculator yet. So, normal force truck equals mg. Normal force truck equals m load times g. That's the conclusion that we get from using the net force y equation. Now for net force x, let's do that in this light blue color. And I'll do it over here. Net force horizontal is equal to mass of the load times the horizontal acceleration of both the load and the truck. So that's mass of the load times, I'll just call it acceleration x of the system, is equal to forces right minus forces left. Well, all we have is a force to the left minus force of friction static. And the force of friction static, assuming the worst case scenario, they were asking calculate the minimum stopping distance for which the load will not slide. Minimum stopping distance means maximum deceleration. What's the highest deceleration we can get? Because with a lower deceleration, you'd obviously have a higher stopping distance. If you're not slowing down as quickly, then you're going to go farther before you stop. So if they're asking for minimum stopping distance, then that calls for a maximum deceleration, in terms of magnitude at least. That would mean we have the highest magnitude acceleration possible. So the highest possible magnitude for acceleration would be at the highest possible static friction. So for this, we don't need the inequality symbol. We just set it equal to the actual maximum. So this is actually equal to force of friction static maximum outright. And so that's going to be mass of the load times the, I guess I will call it acceleration maximum. I'm beginning to regret this. I'll change the name back to acceleration x of the system. Equals minus coefficient of maximum static friction times the normal force. In this case, it's the friction between the load and the truck, so we would use the normal force between the load and the truck. The normal force between the ground and the truck is, well, between the ground and the truck. It should have nothing to do with the load. So that's how you know, in situations with multiple normal forces, which one to use when calculating your friction. The normal force used to calculate your friction is also the normal force that is exerted by the surface against which you have that friction. So that would be normal force truck, which we just calculated is equal to the mass of the load times g. So if I do mass of the load times acceleration x of the system, yeah, I don't want to call it acceleration max, that was poor planning on my part, equals negative 0.5 times normal force truck was equal to ml times g. Oh, and would you look at that? Divide both sides by the mass of the load. You don't even need to know the mass of the load. The mass of the load doesn't even matter. And so it's just negative 0.5 g. The acceleration is negative 4.9. The acceleration horizontal of the system would just be negative 4.9 meters per second squared, or in other words, 4.9 meters per second squared in the opposite direction to where the truck was initially moving. Okay, so that is only part of the solution because they didn't ask us for the acceleration, they asked us for the stopping distance, and for that we can just use kinematics. I think I can probably squeeze that somewhere onto this same page. How about down here? We've got a little bit of space. Should still be visible on the camera screen. Let's see, so I would use third equation of kinematics because I know three things. I know V initial, and because it's stopping distance, then we know V final must be 0, and now we know the acceleration, and the third equation involves those three variables along with displacement. So V final squared equals V initial squared plus 2 times the acceleration times the displacement. I guess I'd call this the acceleration in x times the displacement in x. V final squared is 0, so that's going to be 0 squared equals 12 squared plus 2 times negative 4.9 times whatever this delta x stopping is. Okay, add, I guess that would be 9.8 delta x to both sides and divide by 9.8. 12 squared divided by 9.8, 144 divided by 9.8 is 14.69387755. I'm just going to round that to 14.69. So delta x stopping equals 14.69 meters. Oh, there we go. Now the pen is working. 14.69 meters. If you don't have at least 14.69 meters, that load is going to slip and probably hit the driver. Wait a minute, but then it would have to actually be like a semi-truck. It would have to be from above the driver, right? Hold on, let me reread the problem. I know this isn't really consequential as far as the physics is concerned, but may slide. A significant hazard for the driver is that the load may slide forward, crushing the cab if the truck stops suddenly in an accident or even in braking. Okay, I guess that would still work in a scenario like this because you would have the load. I guess it would slide forward, and if it's heavy enough, it can probably, just crush through here and still hit the driver in the back of the head instead of from above their head. Okay. I can see that, especially if the back of the car has like glass. They did say that the load could be something like steel beams, and yeah, those beams could fit through a window, just break through a window and hit the driver in the back of the head. Okay, I can see that. Well, that takes us to the 2-hour mark. So I guess we'll do, since I can't find one in the book, hold on, let me grab the other book. Maybe it has a problem that has like multiple blocks, kind of like what we did earlier. And if it doesn't have that, then we'll just go back to the actual exercise from the course plan. Give me a minute. I kind of doubt it. I don't remember this other book having any friction problems that involved multiple objects connected by a rope, except of course ones that involve ramps and pulleys, which I'm trying to avoid. Ah, close. That one has 3 carts on a frictionless surface. Okay, let's try one of these other force chapters then. Oh, I see one of the types of problems that I'm going to want for later. But not what I'm looking for right now. Also a no. And that's also a no. Okay, I think I'm just gonna... Oh, wait. Ah, man, it even says on the diagram no friction. Wait. Oh, okay. There is some friction between the objects, but not between the objects and the ground. Ah, that might be for later as well. Man, they really love their frictionless surfaces. Okay, fine. We will use one of the problems I wrote. I mean, I guess I wrote them for a reason. Okay, let's switch back to the screen over here. So for those who are looking for these problems, again, link in the description to the course plan. If you scroll down to the force section, Unit 3, you will find under practice, I'm going to be looking at this friction one. And that will open this for you. So it says 3 objects are being pulled along a rough surface by a force of 180 newtons. The surface has a coefficient of kinetic friction that is equal to 0.1. Find the acceleration of this system of objects and the tensions in the ropes. Bonus question, what is the minimum coefficient of static friction needed if we want to keep this system from moving? And I'll just do part 1, and number 2 you guys can do on your own as an exercise. I do have the solutions after all. You can just click these little solution videos linked in the parentheses. So yeah, let's go ahead and switch back to our document camera and flip over to a new page. And first thing I'm going to do, of course, is copy our diagram. So we had 40, 50, and 30. So here's our overall diagram, 40 kilos and 50 kilos. Wow, that was a very weird looking 5. I think I saved it. And 30 kilos. and they're connected by ropes. And there's an overall applied force of 180 newtons. There's an overall applied force given to us as 180 newtons. And it says the surface has a coefficient of friction of 0.1. So we've got a rough surface for which the coefficient of kinetic friction is 0.1. Coefficient of kinetic friction is 0.1. Okay. Find the acceleration of the system and the tensions in the ropes. Well, 3 objects call for, I've said it before and I'll say it again, 3 objects, 3 diagrams. 3 objects require 3 diagrams. So we've got our 40 kilogram object, our 50 kilogram object. I should probably write the mass first and then draw the box around it. If I draw the box first, I might not leave enough space. And actually, speaking of space, I don't think I left enough space horizontally here, but we'll see. And 30 kilograms. Okay, draw the forces acting on each one. So we have the 180 newtons. I guess I'm going to start from right to left this time. We've got the applied force. I guess I don't have enough space to write down the 180, but we'll copy that over later when we actually write equations. We have force of gravity, of course. 30G. And I guess for this one, should I use 10 for G? Yeah, let's use 10 for G. I'll use G equals 10 meters per second squared just to speed up calculations. So we'll do 30G down, and then there's got to be some normal force up. I guess I'll call this normal force 3 since this will be object 3. I'm thinking of them as object 1, 2, and 3 in that order. So I'm going to call that normal force 3. And I guess these would be ropes 1 and 2. So I guess this would be connected to rope 2, so that's going to be force of tension 2. And it's going to be, of course, towards the direction of the rope, so to the left. And I did not draw this to scale. If I did, then the applied force would be greater than tension 2 at the very least. And we are also missing friction. They said it's kinetic friction, so we know that it's opposite to the direction that the system would be moving. In the absence of friction, which way would the system move? If it was, just sitting there alone, and then suddenly somebody came and applied a force on it to the right, is there any scenario where that would cause the object to start moving to the left if the object wasn't moving left to begin with? Nope. So over here, the assumed direction of motion would have to be to the right, which would mean that the kinetic friction would try to oppose it and would be to the left. So that's going to be force, friction, kinetic, and I guess we're going to call that force, friction, kinetic for object 3. Okay, next object. You know what? Okay, I'll do number 2. I was going to skip back over here and go back to left to right, but we'll commit. Right to left it is. So, object 2, we've got, of course, force of gravity, so 50g, force of gravity. And we're going to have, I'm going to call that normal force 2. It's got force of tension 2 pulling on it to the right. It's going to have force of tension 1 pulling on it to the left. I would assume force of tension 1 is smaller than force of tension 2. Otherwise, the system wouldn't be able to accelerate to the right. And that just doesn't make sense. Well, it could make sense if the system doesn't accelerate at all. So those are your 2 scenarios. If I apply a force to the right on a system which was presumably at rest before this applied force came into the picture, then the only things that could happen is nothing if the static friction is strong enough, or motion to the right. Those are your only 2 possibilities. And then friction kinetic would have to be to the left. For all 3 of these, the kinetic friction would have to be to the left, because all 3, if they move at all, would be moving to the right. So force, friction, kinetic for object 2, that's going to be to the left. And I think that's everything. No springs to worry about. No physical contact with anything other than the ground, so that's the only normal force. Both ropes are accounted for. Yeah, we're good. Okay, next diagram. Force of tension 1 to the right. Of course, 40g downward. Normal force 1 upward. Force of kinetic friction 1 to the left, and that's it. There's no rope or pushes or pulls coming from the left-hand side of that block, so we are done. At least with the diagramming phase. Now we get to writing equations. So we've got, of course, 3 sets of equations. Because it's a 2-dimensional problem, you have to write an x and a y. So net force y1, net force y2, and net force y3 are all going to be rather simple. There are only 2 vertical forces for each block in this problem, so nothing too complicated. And we also know what the vertical acceleration is. It's going to be 0 because we have no reason to believe that these blocks accelerate up or down. So that's m1 times 0, m2 times 0, and m3 times 0 equals forces up minus forces down, so normal force 1. Whoops, not equals, not an equal sign, minus m1g, which is 40g. I'm going to use 10 for g, so 40 times 10. Normal force 2 minus m2g, so that's 50 times 10. And normal force 3 minus m3g, so that's going to be 30 times 10. Okay, so normal force 1 would have to be equal to 400 in order for this to be 0. Normal force 2 would be 500, and normal force 3 would be 300. So normal force 1 is 400 newtons. Normal force 2 is 500 newtons. And normal force 3 is 300 newtons. And we actually need these normal forces, even though we weren't told to calculate them. We're going to have to calculate them anyway, because that's the only way we can calculate the friction forces. So now for the horizontal, net force X for object 1 and 2 and 3. Net force X for object 1 is going to be mass 1, so 40 kilograms, times the acceleration of object 1, which is going to be the same as the accelerations of objects 2 and 3. I'm just going to call that acceleration of the system. Equals forces to the right minus forces to the left. To the right, I've got tension 1. To the left, I've got force of friction kinetic 1, which is, did I say to the right? To the left, I have force of friction kinetic 1. So that's minus, and then force of friction kinetic is coefficient of friction kinetic times normal force, specifically normal force 1 in this case. And that is it for object 1. For object 2, we've got 50 kilograms times the acceleration of the system equals forces to the right, that's force of tension 2, minus forces to the left, I've got tension 1, and I've got friction 2, which is coefficient of friction times normal force 2. And 30 times acceleration system for object 3 equals force to the right. We've got force applied, which I can substitute in as 180 later. And then minus, we've got force of tension 2, and also minus friction 3, which is coefficient of friction, times normal force 3. Okay. We can do the same thing we've been doing all day today. We can add the 3 equations together, and that will cancel out 2 of our 3 unknowns. What are the unknowns, by the way? We know the coefficient of friction and the normal forces we just calculated, so those are known. We know the applied force, it was given to us. So the unknowns are tension 1, tension 2, and the acceleration of the system. So that's going to be, let's see, 40 plus 50 plus 30 is 90 plus 30 is 120 times the acceleration of the system equals force of tension 1 and minus force of tension 1 are going to cancel out. Tension 2 and minus tension 2 also going to cancel out, so those are gone. And I'm left with my positive force as my applied force. Minus, I've got minus coefficient of friction times normal 1, and same thing times normal 2, and same times normal 3. I can factor out the coefficient of kinetic friction and just do normal force 1 plus 2 plus 3. Do I need to do it this way? No, but factoring it out helps you see the big picture. What do we have now? What is this? This is the net force equation of a 120 kilogram object that has an applied force and just one big friction force acting on it. This is net force on the system. If I were to draw a diagram that matches this equation, I would have this. I would have a 120 kilogram object that has some applied force on it and has some friction, mu k, times normal force system. And the normal force on the system would just be the sum of the three normal forces on the individual parts. So normal force system would just oppose the gravitational force on the system. Gravitational force on the system, which is equal to the mass of the system times g. And does that make sense? Well, yeah, 40 times 10 and 50 times 10 and 30 times 10 would be 120 times 10, so that would be 1200 newtons, and then the normal forces 1, 2, and 3 add up to 400 plus 500 plus 300. Yeah, that's also 1200. So yeah, it checks out. Again, not the most necessary thing to learn from this lesson, but it helps. Of course, if you're struggling with other stuff, I would prioritize reviewing that other stuff first. But once you have the time, this is worth it. It's just not so worth it that you should prioritize it over the more important ideas. As long as you can at least do it this way, just step by step, you're good. You don't need to worry too much about this if it feels like you're drinking out of a fire hydrant right now. This picture will start to develop in your mind over time. Anyway, we've got 120 A system equals force applied minus coefficient of kinetic friction times the sum of the normal forces. So if I go ahead and continue that, I guess we'll do it over here. We've got 120 acceleration of the system equals force applied was 180. Oh, I guess this angle for the lamp is not really good because when I write, I'm blocking the light directly. I'll have to experiment and figure out something. But at least what I like about this angle, because if I put it at the other angle, the lamp is just gonna cast a shadow from the, what do you call it, the document camera stand, and that's gonna leave that little shadow in the corner that you saw in the past 2 or 3 sessions, and I didn't like that. But maybe I'm worrying too much about nothing. I mean, I am gonna move my hand out of the way after I'm done writing, so it's not the end of the world. Where was I? Minus coefficient of friction, so minus 0.1 times the total normal force is 1200. So 1200 times 0.1, well, that's easy, that's 120. And 180 minus 120 is 180 minus 120, that's 60. So 120 times the acceleration of the system is equal to 60 newtons, and 60 divided by 120, the acceleration of the system must be 0.5 meters per second squared. Okay, so that answers the question, the main question. The bonus question is, what is the minimum coefficient of static friction needed if we want to keep this system from moving? What is the minimum coefficient of static friction needed to keep this system from moving? So in other words, to give this system an acceleration of 0 with an initial velocity of course, 0. what would the static friction need to be in order for the acceleration to be 0? What is the lowest static friction coefficient that would make that possible under an applied force of 180 newtons? What's the lowest static friction coefficient needed to block 180 newtons of force from moving my system? So actually, I don't have to change much of anything. The direction of the static friction would have to still be to the left, so the only thing that changes as far as my diagrams are concerned is that I change the friction from kinetic to static. And then as far as my equations are concerned, these all become zeros. So really what I would have is, it would just end up as this again, except over here I would just have to write this as mu static times my sum of the normal forces. So 120 times 0, 120 times 0 would equal force applied, I guess I should have subbed that as 180, but we'll do that on the next line, times coefficient of static friction times 1200, the force applied being 180. So if I add this over to the left-hand side, so that's a 0, so I've got 1200 mu static is equal to the force applied, which is 180. If I do 180 over 1200, 180 over 120 would have been 1.5. So 180 over 1200 is a tenth of that, is 0.15. So mu static, oh, actually, the way I should be phrasing this is, let me think, how do I want to word this? Well, okay, let's carry on with this calculation first. So 180 over 1200 is going to be 0.15. And this is actually the minimum coefficient of friction needed, but I didn't write it as an inequality, so let me see how I would want to fix that. So the way I would have to go about fixing that is to say that I would have to say that the force of static friction maximum has to be greater than or equal to the force applied, because that's the only force that needs to be canceled horizontally. All the other forces, the tensions, all cancel each other out. So force of friction static maximum has to be greater than or equal to the force applied. So mu static maximum has to be greater than, or no, mu static maximum times the normal force of 1200 has to be greater than or equal to 180, and then if you divide, you get mu static maximum has to be greater than or equal to 0.15 if we do that division again. So yeah, it has to be at least 0.15. Okay. Anything else I want to say about this before moving on? I mean, most teachers, and even the AP exam itself, isn't really going to have you use inequalities for static friction. But I still like to use it because it helps you remember that static friction is one of those inequality forces, just like normal force and tension force. I feel like it's important to remember that, at least conceptually. But if that's too overwhelming for you, I guess I can give you a little bit more of that, what did I call it earlier? Problem writer psychology, or whatever I called it. When they ask you what's the maximum or minimum value of whatever associated with things like friction, if you just use an equal sign, you're going to get the exact number that they want, and you don't have to worry about confirming that it is indeed the maximum or the minimum or whatever they specified. In most cases, it'll just work out without you even having to worry about lower values if it's a maximum or higher values if it's a minimum. So yeah, they don't really care, but I do. I don't know if that's a good thing or a bad thing, but I guess that's just one of the many disagreements that people in the realm of physics can have. Okay, we've got we can do about half an hour, so I think I can introduce the problem of inclined planes, and we will just resume from there next time. Is that actually... Yeah, that's going to be on the next homework that I have in like the practice section. So yeah, let's go ahead and do that. Let me see, do I have a... Okay, I've got a simulation I can show off. Actually, I've got two of them, and I'm not sure which one is better because I didn't really have the time to test the two and compare them. But we can do both. So in this FET simulation that you're seeing here, we've got a filing cabinet. Can I zoom in on this? Is there... I don't see... Yeah, I don't see a way to zoom in on it. Well, if you squint at it a little bit, you can probably see they've shown a normal force pointing in this sort of diagonal direction up and to the left, and they've got a friction force pointing up and to the right, and they've got weight or gravitational force pointing straight down. Actually, I can adjust. Yeah, there we go. That might be better. Oh, and I just got it to start sliding. Don't want that. Yeah, there we go. I think that's a little bit better. A little bit easier to see, I would hope. Can I actually just... No, I can't. Yeah, I can't zoom it in using the browser. Oh well. So this right here is a classic inclined plane situation. You've got three forces. You've got a force of friction that's parallel to your incline, which I guess, according to this, is at 15.4 degrees right now. You've got a normal force, which of course is perpendicular to the surface. That's why it's slightly angled. We're used to it being straight up, but that's because we're used to having our objects on a flat, level surface. If you lift the surface up by 15 degrees, then the normal force will also tilt by 15 degrees so that it's always at a 90-degree angle to the contact surface. But the force of gravity doesn't care, which is why, as you can see in that blue arrow over here, it still points straight down. So what do we do in a situation like this? Well, we have two options. We could continue doing net force X and net force Y using right and left as our X directions and up and down as our Y directions, but then that would mean that we have two forces that would need to be decomposed. We've got the friction force is a little bit up and to the right, so we would have to break that into a rightward component and an upward component. and normal force is up and to the left, so we would have to break that into an upward component and a leftward component, and that's a lot of work. I mean, we've done it before, but this type of problem is so common that it would be better if we could find a way where we wouldn't have to do that much work every single time we encounter this. So, there is another approach we can take. Instead of using x and y, we can just rotate our coordinate system by, in this case, 15.4 degrees, and instead we can use two new axes. Instead of x and y, we can use whatever this direction is, parallel to the incline, and also this direction, perpendicular to the incline. Some people like to call this parallel direction the new x direction, while they call this perpendicular direction, lining up with the normal force, they call that the new y direction. And then, regardless of whether you call them the new x and new y, or you call them parallel and perpendicular directions, what you're left with is two of the forces are already on your new axes, the friction and the normal force, and only one force, the weight, would have to be broken into components. So let's go ahead and see how that can be done. Let's go ahead and see how that can be done. So we have, I guess I'll draw it over here. Actually, no, I'll draw it here. And I'll draw it with the incline going down and to the right. Okay, so you have an inclined plane or ramp or just an incline, whatever you want to call it, or a slope. It's going to be at some angle, theta. And we're going to have typically an object, sometimes multiple objects, over here. Sometimes the incline will have friction, and other times it will be frictionless. In the example we saw, there was friction, so let's go ahead and stick with what the example gave us. What kind of friction was it if the object wasn't sliding? Of course, that would have to be static friction. And the diagram showed friction up the incline, which makes sense because in the absence of friction, you would expect this to just slide down. So you have force of friction, static up the incline. You have normal force, perpendicular to the incline and away from the incline. Normal force is always a push. It does not pull, so it has to be away from the contact surface. And force of gravity is straight down. That G is looking like a Y. I think that fixes it a little bit. So yeah, figuring out all the geometry and trying to break normal force into a component horizontal and a component vertical like this, and then doing the same thing for friction and breaking it into components. Doable, but not very helpful. Instead, the better approach is to have a new coordinate system. Instead of using this x and y coordinate system that we've been using up to this point, we can use a coordinate system that looks more like this. And it's up to you whether you want to consider up the incline or down the incline to be the positive direction, but your two directions are now perpendicular to the incline and parallel to the incline. I would hope you remember these symbols from geometry, right? This is the symbol for perpendicular. And that's the symbol for parallel, in case you've forgotten it. This also reminds me how parallel is spelled. Parallel is spelled with 2 L's in the middle. But yeah, up to you whether you consider the down parallel or up parallel direction to be positive. I guess it depends on the problem. If you're working with a problem where an object is sliding down and you want to figure out how fast it's moving and how far it travels, maybe in that case it makes more sense for down the incline to be your positive direction. If you're kicking something up the incline, then maybe in that case it makes more sense for up the incline to be your positive direction. You can just make your own judgment based on whatever situation is given to you. And I will probably do the same once we look at some examples. The point is, if we adopt this new coordinate system, now we already have our force of friction along one of our coordinates, and we already have our normal force along one of our coordinates. Now it's only the force of gravity that needs to be broken into components, and the force of gravity can be broken into components that will look like this. A component that is parallel to the incline and down, and a component that is perpendicular to the incline and down. And to do that, we're going to need a bit of geometry. We need to figure out which of these is going to be the cosine component and which of these is going to be the sine component, and what angle to even use. Let's go ahead and draw another copy of this. So here's the angle theta, and this time I'm just going to draw the gravitational force alone, and I'm going to leave all the other fluff out of it. So here's the force of gravity, and I'm going to draw it all the way down like that. And I'm going to draw the components that I want to get, which are going to look like that. And let's see what we can do. So I know that if this is theta, then this angle over here has to be 90 minus theta, has to be 90 degrees minus theta, because this over here makes a right triangle. Also, I know that if this component is parallel to the incline and this component is perpendicular to the incline, then those components must be perpendicular to each other. So this angle plus this 90 minus theta must add up to 90 degrees. So what's this? I guess I'll call it x for now. Actually, maybe not x. Let's call it alpha. So alpha plus 90 minus theta has to add up to 90 degrees. And if I go ahead and solve for alpha, then alpha equals 90 minus, I'm going to subtract all of that 90 minus theta. 90 minus 90 cancels out, and then minus negative theta. Alpha is equal to theta. So this angle is actually theta again. So I'll copy it over to here. This angle is equal to theta. The angle between the force of gravity and the direction of its perpendicular component is the same as the angle of the incline. And there's a more intuitive way that you can think of this. If you think of it as starting with, a block on a flat surface, if you think of it as starting with a block on a flat surface, like that, with the force of gravity straight down. So here, the perpendicular direction to gravity is the same as the direction of gravity, but if you that start tilting this up. If you tilt the, I guess you could say the floor, for lack of a better term, if you tilt the floor upward, then you are also tilting, I guess I'll use another color here. I'll use blue for the direction of the perpendicular. Yeah, I'll use blue for the direction of like the perpendicular axis. What you've essentially done, force of gravity continues to be straight down. But this perpendicular axis will have tilted by the exact same amount that you tilted, well, the whole entire floor. So I guess it's easier to visualize with like a book. So here's a book, and I've got, my hand is going to represent like the perpendicular direction. So if I lift the book by 10 degrees, then my hand also tilts by 10 degrees. If the book tilts 30 degrees, my hand is also tilting 30 degrees with it. However many degrees the book rotates, my hand, which is perpendicular to it, also rotates by that same amount. So that's another kind of more intuitive way to convince yourself that this is true, that the angle between the direction of the perpendicular component and the gravity is just the angle of the incline. The gravity direction, you could say, is just a sort of constant, unchanging reference, so any changes with respect to it, well, I'm struggling to find the perfect way to word that sentence, but I think you can get the gist of what I'm trying to say. Coming up with the right words right now is kind of hard for me for whatever reason. Maybe my brain is too fried from streaming for too long. But yeah, that gives us the recipe that we need to break our gravitational force into components. So now all that's left is to actually write out what these components are going to be. So this component is adjacent to my force of gravity. This component, or did I say adjacent to my force of gravity? Adjacent to my angle theta over here. This component is adjacent to this angle. So that's going to be the cosine component, while this component over here, by process of elimination, would have to be the sine component. So this is force of gravity cosine theta, and this is force of gravity, make that F a little bit bigger, force gravity sine of theta. So anytime you have a problem involving an inclined plane, if you know the angle of the incline, which will typically be this bottom angle, if they give you the top angle, then you have a little bit of work to do, which is just subtracting it from 90, I suppose. But otherwise, your go-to is break it into components. The component parallel to the incline is going to always be pointing down the incline and parallel, and it's going to be mg sine of this bottom angle, while this component presses into the incline and is equal to mg times cosine of this angle at the bottom. The only other twist that you might occasionally encounter with inclined plane problems is you might encounter additional forces that are not necessarily on this parallel or perpendicular axis. I have a problem, for example, where, I guess I'll draw it over here. I have a problem in one of my books where they give you this and then they say, oh, somebody applies a force parallel to the ground like this. There's a force applied like this, and of course you're going to have to do some geometry and break that applied force into a component perpendicular to the incline and a component parallel to the incline. And I would hope that you have the geometry skills to do that, but if not, we will see an example of that. I do plan on doing that problem at some point. I may have already done it in one of my older review videos. I'm not entirely sure. It's not like I have all of my uploaded content memorized. That's the thing. I worry about what'll happen when I get to the point where I've done most of the good problems in my books. I guess I'm going to have to start writing a lot more of my own. Which might not be a bad idea, as long as I actually take my time and carefully consider the consequences of the numbers I end up choosing, because when I do it on the spot, oh boy, do I come up with some ridiculous numbers. But yeah, I think this is where we will have to leave it for today. So if you want to try and do some calculations with these, you can feel free to test out your skills on that homework set that I had on the screen earlier. It does come with a solution video, so you can always check your work. So yeah, actually, let's make that homework. Yeah, let's make that homework. Your homework is to actually try doing, let me see, where is it? Your homework is to actually try these inclined plane problems right here. So this is what? Homework PDF number 19, which you can access right here in the course plan. And also, I guess I haven't been talking about it a lot lately, but reading and exercises in the book, that's also something you might want to look at. I think we've covered almost everything, so anything as long as it doesn't involve pulleys, you should have enough now to be able to at least make some decent attempts at some of them. So what we have coming up next, so for next week, of course we're going to do some inclined plane problems with and without friction. So actually, go ahead and do inclined planes, and you might as well look at inclined planes with friction. It doesn't change too much when you add friction to the mix. It's just one more force to put into your diagram. So yeah, I don't think it would be too much of a stretch to ask you guys to at least look at one or two of these, if nothing else. And that'll be the plan for next time. We'll do some inclined plane problems, inclined planes with friction, and then we will introduce pulley problems, and we will talk about the assumptions that we make when it comes to pulleys, and how we will end up correcting those assumptions once we get to rotational dynamics. For the force chapter, we are not going to account for the rotation of the pulley. The rotation of the pulley is going to cause a little bit of trouble for us, so we're just going to assume that the rotational effects are negligible, and that will allow us to make a certain assumption. I will talk about that when we cover pulleys, which will in all likelihood be next week, because I don't see us taking that long on doing inclined plane problems. And if we're going to discuss pulleys, I would imagine we would also make it far enough to just put it all together and do just straight up pulley problems with all of it. Inclines, friction, systems, the whole shebang. And after that, we'll just be doing a lot of problems. Just lots and lots of problems, which might be another 2-3 weeks, depending on what I want to include in my list. I'll have to reflect on it and see what I want to do, and knowing me, I'm probably not going to figure it out until like the day before I have to actually start streaming that section of the course, but it's fine. I've done this on the fly before, so if that's what it's gotta be, then that's what it's gotta be. Any other suggestions for studying? Did I talk about the book? Yeah, you can look through the book. Let me see, chapters 4 and 5. So if I open this, chapter 4, normal tension and other forces, okay, and then chapter 5 has friction and, oh, well, I guess we can talk a little bit about the spring force, although I'm probably going to leave that until the next chapter, the energy chapter, where springs play a more important role. And drag forces, we can talk about at least a very, very specific case of air resistance that you can solve in AP Physics 1, and I guess I will just allude to what will happen for the AP Physics C students. Again, in case you didn't watch the first video in this whole live stream series, I went over how I'm not going to do the calculus-based parts of Physics C until we're done with everything algebra-based. So I guess it doesn't hurt to reiterate on that. Once we get to the end of... where is it? Once we get to the end of simple harmonic motion, that is where Physics 1 and Physics C will diverge. So for Physics 1, we're going to carry on with fluid mechanics. For Physics C, we're going to start reviewing everything, but with calculus. So it'll probably be, I still haven't fully planned it out, but it will probably be just covering multiple chapters at once, because I don't think the calculus is going to take too long for each of these chapters individually. We will probably be able to do like 2 or 3 of these units at a time, or maybe the approach is going to be that I'm just going to pick out some calculus-based problems and go in the order of just the order that you see here. I'll think on it some more. But we'll have something ready to go. And if you don't have the patience for that, then you might want to look through, again, my older videos might have some calculus-based stuff that the AP Physics C students can look at for mechanics. And in case I didn't mention it, E&M students, sorry, but I don't think I'm going to have anything for you this year. Not in time for the AP exam anyway. But we'll see. I would like to review a couple of things for E&M just so that I can teach it a little bit better, because while it is one of my specialties, while I do know it better than other branches of physics like thermal physics and nuclear and modern physics, I have had some problems that I feel like I should be able to do more easily than I have been doing them, so I might be in need of some review there, but that is a problem for me to worry about later. I think I will stop rambling now. Hope you guys learned something helpful today. Don't get too overwhelmed by all of that stuff about, the big picture system stuff. Just know that it exists and kind of let your brain process in the background and let the pieces fall into place on their own, so to speak. And yeah, just keep practicing. Don't forget to do your homework, whether it's homework assigned by me or by your teacher if you're taking this in school, or, well, I guess it depends on how good your teacher's homework actually is, but that's neither here nor there. And yeah, just don't forget to practice. And if you need to look back on some of the old videos for some of the older topics that you might need a refresher on, I did give this warning last week and I will warn again. We are going to do problems in this fourth chapter that will involve kinematics. So if you've forgotten your kinematics, then make sure that you are reviewing that, because the time for that will be coming. And it might be sooner than you think. And with that, I believe I can now send you off. Class dismissed.